The F-100 is one of our primary tactical support weapons systems. This aircraft has a proven history of outstanding performance. One of the reasons for this dependability is the rugged power plant. The One, a high-performance aircraft, is adaptable to many missions. It is used for reconnaissance, as a tactical fighter, and as an interceptor. Approximately 30,000 pounds of thrust is developed by its twin engines. The F-102 is the first operational Air Force Delta Wing aircraft. The performance characteristics of this weapon system are ideally suited for intercept missions. A reliable power plant is essential for the success of any mission. The F-102, 101, and 100 are all powered by the rugged J57 engine developed by Pratt & Whitney. The individual engines vary somewhat, but for the most part are the same fundamental design. The J57 is a dual compressor engine. The engine consists of the following components: the inlet, the low-pressure compressor, the high-pressure compressor, the diffuser case, combustion chamber, the first, second, and third stage turbines, the afterburner, and the exhaust nozzle. The low-pressure compressor, referred to as N1, is driven by the second and third stage turbines. The high-pressure compressor, N2, is driven by the first stage turbine. These two units, or spools, are not mechanically connected. The J57 operates on the same basic principle as all jet engines. Pressure, presented in graph form below the basic engine outline, and velocity are increased by a series of rotors in the compressor section. A compressor bleed system prevents compressor instability when the engine is operating at reduced power. The compressed air passes through the diffuser into the combustion chamber, where the air expands, thus reducing somewhat the velocity and pressure. Fuel is mixed with a portion of the air to form the combustible mass. When combustion occurs, the gases are expelled through the turbines. At this point, power is extracted by the turbines to drive the compressors. The remaining energy, expelled through the exhaust nozzle, provides the thrust. Since exhaust nozzle and turbine discharge pressures are relative, turbine discharge pressure is used as a parameter to determine thrust. Thrust is the measure of force developed by the engine. Force is determined by mass times acceleration. Mass is the weight of air and fuel passing through the engine. Acceleration is the difference between inlet and the turbine discharge velocities of this mass. Thus, thrust may be expressed by the formula force equals mass times acceleration. The engine trim charts are based on this formula. Additional thrust is obtained in the afterburner by increasing mass and acceleration at that stage. The basic engine pressure ratio during afterburner operation is maintained by increasing the exhaust nozzle area. Efficient engine operation depends on correct fuel scheduling. The basic components of the J57 main engine fuel system are fuel pump and fuel pump transfer valve, fuel control, and the pressurizing and dump valve. The fuel pump is a dual-element spur gear pump. One element supplies fuel to the afterburner, the other to the main engine. The fuel control meters the fuel required to operate the engine through its full range. The pressurizing and dump valve supplies the main engine fuel manifold and drains the manifold at engine shutdown. At engine start, fuel enters the pump through the impeller where the pressure is increased. This provides a positive pressure head to the main stage. At this stage, the fuel reaches output pressure. The pressurized fuel closes the fuel regulating transfer valve and the afterburner check valve and flows into the fuel control. The main metering valve is closed at this time. A portion of this fuel passes through the minimum flow orifice through the signal line to the P&D valve. Since the control is in bypass, pressure does not build up enough to close this valve until the power lever moves from cutoff to idle. When the power lever is moved to the idle position, the fuel dump valve closes. The main metering valve opens. The cutoff valve moves off its seat. The pressure loading valve opens. The P&D valve inlet check valve opens. And the fuel is supplied to the primary side of the fuel manifold through the pressurizing and dump valve. At approximately 74% RPM, the fuel pressurizing valve will open to supply fuel to the secondary side of the fuel manifold. The J57 engine uses a primary and secondary system in order to obtain the highest possible fuel flow with the shortest possible flake. At low RPMs, only the primary side is used. When the emergency system is selected, the actuator positions the pilot valve to direct pressure to the shuttle valve piston. The shuttle valve blocks off metered flow and provides a port for unmetered fuel to the emergency throttle valve. This mechanical valve controls the flow of fuel. The afterburner element of the fuel pump will supply fuel to the engine in the event of main element failure. The primary function is to furnish fuel for the afterburner. The other components of the J57 afterburner system are the afterburner fuel control, exhaust nozzle control, igniter valve, and the mechanical shutoff valve. The relative position of the components varies according to engine model. The afterburner fuel control meters fuel to the AB spray bottles. The exhaust nozzle control directs compressor discharge air to open and close the nozzles. The igniter valve injects fuel into the combustion chamber, creating a streak of flame to ignite the afterburner. In the event of electrical failure, the mechanical shutoff valve will terminate AB operation at approximately 80% RPM. Rotation of this valve causes AB stage fuel to bypass through the AB fuel control regulator valve. The fuel control unit is carefully calibrated on the test bench to assure accurate engine fuel scheduling. The main functions of the fuel control are to maintain acceleration schedules below compressor stall zone, to prevent over-temperature during acceleration, prevent lean die-off during deceleration, and to maintain any selected engine speed within operating limits, regardless of altitude. The fuel control senses engine RPM, inlet temperature, and burner pressure to supply the correct amount of fuel for any ambient condition. When calibration has been completed, all external adjustments, except the idle and military trim screws, are sealed. These seals are installed to protect test bench precision calibrations and must not be removed. The J57 engine will provide relatively trouble-free operation when all systems are functioning correctly. However, the systems must be properly rigged and adjusted. One of the most critical engine adjustments is the rigging of the fuel control linkage. Full range movement is obtained only when the fuel control and afterburner mechanical shutoff valve levers are correctly positioned. The levers are set to predetermined angles. A protractor or etched template is used to set the linkage at these angles. The protractor is positioned at the oil pump and accessory housing plug to establish a reference angle. This reference angle will be used to adjust the fuel control lever. With the fuel control lever in cutoff position, the difference between the reference angle and this reading must be the number of degrees specified in the tech manual. It may be necessary to readjust the fuel control lever to obtain the correct angle. The fuel control lever and serrated spacer are ratcheted to give the desired angle. The fuel control position, which, when all other linkage is connected, will close the afterburner mechanical shutoff valve. The power actuating rod is then attached to the fuel control lever. Move the mechanical shutoff lever to the detent position. The rod, connecting the cross-shaft lever and mechanical shutoff valve lever, may have to be adjusted to the specified length. The AB mechanical shutoff valve is held in detent position, while the lever is ratcheted to the position where the rod, which has already been adjusted to the specified length, will fit. Then all connections are tightened. Either the protractor or an etched template is used to again check the angle of the fuel control lever. It may be necessary to readjust the fuel control lever to obtain the correct angle. After corrections are made, all connections are then safety. Replacement or adjustment of most components will affect engine operation. Prior to aircraft installation, the engine is thoroughly inspected and tested to ensure satisfactory performance. A fuel leak check is imperative before initial start of a repaired engine. With the system pressurized, check all fuel lines and connections. The exhaust nozzle opening must also be rechecked before initial engine start. Nozzle diameter not within specified limits will affect engine efficiency. On some engines, a fail-safe device is installed to prevent total loss of power in the event of linkage failure. The device will position the fuel control lever to a 45-degree angle setting, which will provide approximately 90% RPM, thus ensuring sufficient thrust to maintain flight. After installation in the aircraft, all airframe to engine connections must be checked and adjusted, and the engine retrimmed. Final trim, to compensate for aircraft installation losses, is preferably accomplished with the aircraft headed directly into the wind. Prevailing wind velocity and direction must be within limits specified in the tech manual. The trim pad area must be free of loose objects that could damage the engine if ingested. To effectively trim the engine, power control settings must be coordinated. Throttle linkage is operationally tested before making fuel control adjustments. Movement of the fuel control quadrant must synchronize with throttle movement. Power control movement is transferred to obtain predetermined fuel control settings. The aircraft manual indicates the relative degree of movement throughout the entire throttle range. Close attention to detail is required when trimming an engine. Changes in ambient barometric pressure and temperature will affect engine performance characteristics. True barometric pressure and correct temperature, both recorded within 15 minutes of the trim run, are used to determine target PT7. Target PT7 is obtained by tracing the temperature and pressure coordinates on the trim chart. Start engine as specified in the tech manual and allow engine and exhaust gas temperature to stabilize. Retard throttle to idle setting. Desired idle speed is obtained by adjusting the idle trim screw. As in all fuel control adjustments, final trim is always in the increased RPM direction. Proceeding with the trim operations, slowly advance throttle to military power. Allow 5 minutes for stabilizing. Caution, do not overspeed or over-temp engine during run-up and stabilization. With throttle set at military power, record RPM, EGT, and the turbine discharge pressure, PT7. If PT7 reading is low, return throttle to idle and readjust maximum RPM setting at the fuel control. Turn the adjustment clockwise to increase RPM in order to obtain target PT7. Advance throttle to military power. Stabilize, then recheck PT7. Return throttle to idle. Check EGT and RPM. Make certain that RPM is within 2% of data plate speed indication. At the completion of the trim run, follow standard shutdown procedures. Accurate troubleshooting depends on a thorough understanding of the J57 engine and its system's functions. Only by correct analysis of the interrelated parameters can the malfunction be isolated. Proficient troubleshooting is the mark of quality. The tech manual outlines the common symptoms of engine malfunctions, the probable causes, and their remedies. Basic parameters used to determine engine performance must also be considered when analyzing problems. These basic parameters are RPM, PT7, and EGT. One of the most detrimental engine malfunctions is overtemping, or high EGT. Perform static checks of PT7 lines and connections and the exhaust nozzle opening. Make sure the anti-icing valves are closed. Then check for instrument accuracy. All static checks have been performed and found satisfactory. Now the engine must be checked for proper trim. As engine approaches military power, check exhaust nozzle for creep. Check to make sure that PT7 has not exceeded target and RPM is within data plate limits. If high EGT still exists, the engine must be removed and a hot section inspection must be performed. Inspect the burner cans for cracks or hot spots. Check fuel nozzles for loose, burned, or missing air caps, and evidence of seal leaks or clogged air holes. Check the first stage turbine nozzle guide vanes for excessive flow. Turbine vanes bowed beyond limits will distort the gas path, causing loss of turbine efficiency. The amount of fuel required to compensate for this loss accounts for the excess temperature. In conjunction with correction of the bowed nozzle guide vanes, or providing they were within limits, additional checks are necessary to assure the problem is corrected. Inspect first and second stage outer air seals for cracks, burned areas, and damage to outer knife edges. Check clearance between outer air seals and turbine blade shrouds. Check first stage turbine dislocating dimensions. The cause of high EGT may have been one major problem isolated at any phase of the investigation, or the accumulation of minor deficiencies requiring several procedures to isolate and correct. Had RPM exceeded data plate limits during initial high EGT troubleshooting trim run, the engine would have to be field cleaned before proceeding with other checks.
Process is intended to restore compressor efficiency. When this operation is completed, retrimming the engine may bring all parameters within limits.
When troubleshooting engine performance deficiencies, it is necessary to consider all three parameters: EGT, RPM, and PT7. As an example, failure to obtain target PT7 can be caused by many things. By comparing the relationship to EGT and RPM, many unnecessary troubleshooting steps can be eliminated. For instance, when all three parameters are low, a fuel scheduling deficiency is indicated. First, check for full travel of the power lever at the fuel control quadrant. Military position must not be less than 54 degrees. The next step is to remove the fuel control and check the position of the camshaft. With camshaft cover removed, lever positioned at 11 degrees, and the temperature sense bulb in a 60-degree Fahrenheit bath, measure the distance from the end of camshaft to the cover flange. This reading should coincide with that on the camshaft depth plate. Tolerances and replacement instruction are included in the engine tech manual. The engine tech manual includes specific instructions for maintenance procedures. These manuals represent a vast accumulation of knowledge and experience. Through individual ability, initiative, and constant use of the tech manual, proper maintenance and troubleshooting procedures can be achieved. This is the goal of the Improved Maintenance Program. The low-pressure compressor, referred to as N1, is driven by the second and third stage turbines. The high-pressure compressor, N2, is driven by the first stage turbine. These two units, or spools, are not mechanically connected. The J57 operates on the same basic principle as all jet engines. Pressure, presented in graph form below the basic engine outline, and velocity are increased by a series of rotors in the compressor section. A compressor bleed system prevents compressor instability when the engine is operating at reduced power. The compressed air passes through the diffuser into the combustion chamber, where the air expands, thus reducing somewhat the velocity and pressure. Fuel is mixed with a portion of mass times acceleration. The engine trim charts are based on this formula. Additional thrust is obtained in the afterburner by increasing mass and acceleration at that stage. The basic engine pressure ratio during afterburner operation is maintained by increasing the exhaust nozzle area. Efficient engine operation depends on correct fuel scheduling. The basic components of the J57 main engine fuel system are fuel pump and fuel pump transfer valve, fuel control, and the pressurizing and dump valve. The fuel pump is a dual-element spur gear pump. One element supplies fuel to the afterburner, the other to the main engine. The F-100 is one of our primary tactical support weapons systems. This aircraft has a proven history of outstanding performance. One of the reasons for this dependability is the rugged power plant. The One, a high-performance aircraft, is adaptable to many missions. It is used for reconnaissance, as a tactical fighter, and as an interceptor. Approximately 30,000 pounds of thrust is developed by its twin engines. The F-102 is the first operational Air Force Delta Wing aircraft. The performance characteristics of this weapon system are ideally suited for intercept missions. A reliable power plant is essential for the success of any mission. The F-102, 101, and 100 are all powered by the rugged J57 engine developed by Pratt & Whitney. The individual engines vary somewhat, but for the most part are the same fundamental design. The J57 is a dual compressor engine. The engine consists of the following components: the inlet, the low-pressure compressor, the high-pressure compressor, the diffuser case, combustion chamber, the first, second, and third stage turbines, the afterburner, and the exhaust nozzle. The air to form the combustible mass. When combustion occurs, the gases are expelled through the turbines. At this point, power is extracted by the turbines to drive the compressors. The remaining energy, expelled through the exhaust nozzle, provides the thrust. Since exhaust nozzle and turbine discharge pressures are relative, turbine discharge pressure is used as a parameter to determine thrust. Thrust is the measure of force developed by the engine. Force is determined by mass times acceleration. Mass is the weight of air and fuel passing through the engine. Acceleration is the difference between inlet and the turbine discharge velocities of this mass. Thus, thrust may be expressed by the formula force equals mass